Hello, in this session we'll go with atomic radius. Atomic radius is the distance from the center of the nucleus to the outermost electron. Center of the nucleus to the outermost electron is called atomic radius, right? So calculation of atomic radius by taking individual atoms is impossible. That's why we go by taking different types of atomic radius. See, the first one is crystal radius, or you can call this as metallic radius. This is only called atomic radius also because most of the elements are metals. So you can call this as atomic radius. So like this, when you are taking, consider this is a sodium atom, this is another sodium atom, this is the nucleus, this is another nucleus. The distance between them is called internuclear distance. The distance between two nuclei is called internuclear distance. Half of this internuclear distance is known as radius. Individual, by taking a single atom and calculating the atomic radius is impossible. So half of the internuclear distance between two metal atoms, there will not be any kind of overlapping, just side by side the atoms will be there, and half of the internuclear distance you can consider as atomic radius, or you say metallic radius, or you can say crystal radius. This is the first one. Second thing is covalent radius. Covalent radius means there should be a covalent bond like this. When a covalent bond is present, this is the nucleus, the half of the internuclear distance, same thing, it is again internuclear distance, half of the internuclear distance you can call that is covalent radius. For example, carbon-carbon distance will be 1.54 angstroms in diamond. Okay, so this distance, half of this 1.54 by 2 is known as covalent radius, 1.54 by 2. In the same way, you can go for one more radius, that is van der Waals radius. In van der Waals radius, what happens is, for example, you are having a molecule. I am taking a Cl2 molecule. Take one more Cl2 molecule. Between them, there is a covalent bond. If you are going to take half of this, that is called covalent radius. But what I am taking is, this is the nucleus, this is second molecule nucleus, and this half of distance is known as van der Waals radius. Van der Waals radius is a half of the internuclear distance between the two nuclei of different molecules. This is one molecule, this is another molecule. Between them we are having only van der Waals forces. When you are taking half of this, that is called as van der Waals radius. Van der Waals radius is generally 40% more than covalent radius. Okay, now 40% it is more than covalent radius. Covalent radius will be 40% smaller than van der Waals radius, you can say. For example, if you are taking Cl2 molecule, this is a Cl2 molecule, this distance will be 3.6 angstrom. Okay, this distance. So half of this 3.6, 1.8 will be the van der Waals radius. These are the three important radius where you are taking half of the internuclear distance. And now one very interesting one is there that we call ionic radius. Ionic radius we are not going to define like this. Here we are defining like half of the internuclear distance between the two metal atoms present in a metal crystal lattice. Here we are saying half of the internuclear distance between the two non-metal atoms which are bonded in a covalent bond. Here we are saying half of the internuclear distance between the two nuclei of different molecules. Okay, but here ionic radius means up to where the nucleus force is working. The distance up to where the nucleus force is working is called nucleus force is working. The distance up to where the nucleus force is working, you can call that is ionic radius. So many interesting questions you can expect here. For example, sodium plus. Sodium plus is a cation. Sodium is a normal atom. Normal atoms are always bigger than cations. Okay, now normal atoms are bigger than cations. And Cl minus and Cl, if you see, anions are bigger than normal atoms. Why so? Here sodium and sodium plus means 10 electrons are there. Here 11 electrons are there, but number of protons case is same. So the effective nuclear charge will be more in case of sodium plus. When effective nuclear charge is more, it can attract the electrons much, so its radius will be small. And here anion's case, you can see, for example, this case you see 17 protons each, but in chlorine 17 electrons are there, here 18 electrons are there. So obviously here effective nuclear charge will be more, so this will be small, and comparatively less nuclear charge, so it will be larger. When same atoms are given and its ions normal atoms are mentioned, in general they will give you like this: x, x, x. One is plus, another is minus. X minus is always bigger than x plus, if all these are same atoms. Okay, x plus, x minus, x if they are mentioned, x minus is bigger than x plus. This is one important point to be noted. Along with this, there is one other possibility of question, that is, look at this: C minus 4, N minus 3, O minus 2, F minus Na plus, Mg plus 2, Al plus 3, and Si plus 4, like this if we are having. All these are isoelectronic. They will be having 10 electrons. Carbon 4 gain 10, nitrogen 7, 3 gain 10, oxygen 8, 2 gain 10, fluorine 9 gained 1, 10, sodium 11 lost 1, magnesium 12 lost 2, aluminum 13 lost 3, silicon 14 lost 4. So all they are having 10 electrons each. When the number of electrons are same, that is called isoelectronic series. In the isoelectronic series, the negative ion, that is anion with more charge, is bigger. Positive ion with the highest charge is the smallest one. So this type of question they can ask you. S minus 2 bigger than Cl minus, bigger than potassium plus, than Ca plus 2. But don't compare sodium plus and Ca plus 2. Sodium plus is of 1:2, 2:2, 2p6 only. And calcium plus 2 means that will be having argon configuration. This will be having neon configuration. So don't compare like this. If you are comparing like that, calcium plus 2 is only bigger. Okay. So this is about the basics of atomic radius. That means types of atomic radius: crystal radius, covalent radius, van der Waals radius, as well as ionic radius. Now we'll go with the trends, how it is going to change in groups and periods. This is one interesting part. If you know this very well, then rest of the properties you can easily explain. First one, how it changes in groups and periods. We'll take groups. Down the group, atomic radii increases. Down the group, atomic radius increases. Remember this line. The reason what you can say is the new electron, newly coming electron, I am simply writing new electron. The new electron will be entering into new energy level. The new energy levels are away. The new energy levels will be far. That's why the radius will be increasing. Down the group, atomic radius will be increasing because the differentiating electron, newly coming electron, will be entering into a new energy level. Okay, now for example, lithium if you see 2s1, sodium if you see 3s1, obviously second level, third level, and potassium if you see 4s1, so fourth level. So for second level to third level to fourth level, the distance will be definitely increasing. So because of this reason, you can say down the group, atomic radius increases. There may be some exceptions. We'll discuss about particular exceptions in the respective groups. In general, down the group, atomic radius increases. You need to remember this point only. Periods. Left to right in a period. Left to right. What happens in a period particularly? I'm taking a simple period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Up to fluorine decreases. Why? The reason is very simple. In all these elements, okay, the differentiating electron entering into the same period, okay, the same, you say, energy level. 2s, okay, now 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5. So the electron is coming into the same energy level, but the nucleus power is continuously increasing. You can calculate even effective nuclear charge. Z star. The Z star of lithium, beryllium, boron, carbon, if you are considering fluorine, effective nuclear charge will be more. Because of that, fluorine atomic radius will be small. Don't compare your neon, because neon cannot show any kind of van der Waals, covalent bonding. So covalent radius is not there. Neon radius will be van der Waals radius, that is always bigger. So forget about neon. And another question you can face is, the biggest atom in any period is always alkali metal. Alkali metals are always bigger, and as you are moving like this, gradually the radius will be decreasing. The reason for the decrease in radius is effective nuclear charge. All newly coming electrons are entering into the same energy level, but the nucleus power is increasing continuously, so the atomic radius will be continuously decreasing. This is one very, very important point. More than this, D block points are important. Scandium, yttrium, lanthanum, actinium, titanium, vanadium, chromium, manganese, so on. We don't need all those. Zirconium, hafnium, niobium, tantalum, chromium, molybdenum, tungsten, like this. Okay, when these kind of elements are there, rutherfordium, dubnium, seaborgium, like this. Okay, RF. So here what happens is, scandium to yttrium, yttrium to lanthanum, lanthanum to actinium, it's a group. Down the group atomic radius should increase, radius increases. Radius must increase, and radius increases here, no question, radius increases. Titanium to zirconium, vanadium to niobium, chromium to molybdenum, that means this is 3D series and this is 4D series. 3D to 4D radii should increases, no problem with us, with any of this. Zirconium to hafnium, niobium to tantalum, molybdenum to tungsten, all these kind of cases where we are saying 4D to 5D, the radii is almost same. The same thing you can notice even here also. There may be small exceptions will be there. In general, what you remember is radii will be same. See this point, this is very, very interesting. Scan 3D to 4D, 4D to 5D, 5D to 6D, the radius should increase. That is happening in case of scandium, yttrium, lanthanum, actinium. But the problem comes after lanthanum and after actinium. The reason is because of the lanthanide elements, because of the actinide elements. Lanthanide contraction and actinide contraction, we are going for that only. Because of the lanthanide contraction, because of the actinide contraction, the nucleus power is still working on them. Because of the nucleus power, extra nucleus power, their radius is going to be almost the same. Actually, down the group it should increase, but because of the lanthanide contraction here, because of the actinide contraction here, their radius is going to be almost the same. So 3D to 4D radius increases, absolutely clear. 4D to 5D radius same, 5D to 6D also radius same. Maybe small exceptions you can notice, but the reason you need to say, after lanthanum we have lanthanides, after actinium we have actinides, because of the lanthanide contraction and because of the actinide contraction, that problem comes. What is the lanthanide contraction? See, if you know lanthanide contraction, then you can say easily actinide contraction the same. Lanthanoid contraction or lanthanide contraction, there is no much difference, don't worry for that. In lanthanide elements, whatever the elements coming after lanthanum, cerium to lutetium, 58 atomic number to 71 atomic number. The outermost electronic configuration will be like this, but 6s2, 5d1 for this 6s2, and this lanthanum will be having 5d1. After that, the electrons are coming from 1 to 14. When the electrons are coming from 1 to 14, into the f orbital, whose screening is very, very less. Why the screening of f orbital is less? Because of its shape. What is the shape of this? Four-fold dumbbell shape. The four-fold dumbbell shape is not having a proper geometry to screen the nucleus power. When 1 to 14 electrons are coming here, that means whenever one electron is coming, the one proton is also joining. That means nucleus power is continuously increasing. But this, for example, if it is the nucleus 1, 2, 3, 4, let us say this is 4f orbital, this is 5d orbital, this is 6s orbital, 2 electrons are here, 1 electron is here, and all these 4f electrons are coming here. But these electrons are not properly screening the nucleus power. Not properly screening the nucleus power means the nucleus is going to attract all these electrons inside. When all these are pulled inside, the sizes gradually decreases from cerium to lutetium. This is known as lanthanide contraction. The same thing you can expect in case of actinium also, from thorium to lanthanum also same thing happens. There 5f orbital. Both are same. Okay, the same concepts. What is the problem here? Actually 4f orbital is inside. Second problem is f orbital shape. F orbital shape is not proper. That's why the nucleus power is working on the outermost electrons, and outermost electrons are taken inside. When they are coming inside, the radius will be gradually decreasing. That's called Lanthanide contraction. Okay, now lanthanide contraction means cerium to lutetium sizes gradually decreases, and here also thorium to lanthanum sizes gradually decreases. That you can call as actinide contraction. So because of the lanthanide contraction, these radius are going to be same, 4d to 5d. Because of the actinide contraction, the same thing you can notice in 5d to 6d case also. These are the important points related to atomic radius. In next session, we will discuss about the next property. Thank you.